Yes, good morning, everybody, and welcome to our bi-weekly SPCL VCast, the second one this year. And I'm super glad that we could convince Haohuan Fu from Tsinghua University to talk about earth science. And Nikolai will introduce him now.
Okay, thank you, Torsten, and thank you for coming, Haohuan. It's a pleasure to have you. So Haohuan is a professor at the Ministry of Education Key Laboratory for Earth System Modeling and in the Department of Earth System Science at Tsinghua University, where he leads the High Performance Geocomputing Group. And he is also the Deputy Director of the National Supercomputing Center in Wuxi. And among his many accomplishments, he is one of the very few people to have won 2 Gordon Bell Prizes, one in 2016 for atmospheric dynamics and another in 2017 for earthquake simulation. So with that, thank you again, Haohuan, and please take it away.
Sure, yeah. Thanks for the introduction, and also thanks for inviting me to participate in this webinar activity that Torsten has been organizing. So you guys can hear me okay? Okay,
yes.
So
yes.
So this talk today is more like a story about in the last I think at least 5 years how we tried to put a quite complicated scientific computing program and Earth system model onto a new supercomputer. I mean, a new supercomputer at that time. Now it's 5 years old, but at the beginning of the project is a completely new supercomputer to the team, the Sunway TaihuLight supercomputer. And in recent years, I think the project has finally come to a stage that we can use it to produce something interesting to the scientists. So that's another part of the title, the multi-century simulation datasets we have generated. Okay, so first, I think I should still talk a little bit about the machine. I think some of you might have already read some of the papers that described this supercomputer. So Sunway TaihuLight, one of the key the key technology innovation we have made for this supercomputer is, of course, this homemade processor. We call it Sunway 26010. So inside this processor, we have 4 identical core groups, and each core group has one management computing management core, which is kind of similar to traditional CPU cores. You can use it for management, and you can also use it for computing. Now, of course, most of the computing power comes from this 8x8 array of computing cores. Sorry, there's is the noise okay to you guys? I mean, there's some other activities going on.
It's perfect.
It's fine.
It's fine. Okay. At least my as long as my voice can be clear to you guys, huh? So this involves some very interesting programming and design challenges for computer science people, because it's a completely different architecture from before. And if you have read the papers, you would know that inside the 8x8 array, we have the rows and columns to enable the inter-thread communication among these different computing cores. So this used to be the fastest supercomputer in the world, with a peak performance of 125 petaflops with over 10 million cores. So if you want to, as Nikolai has introduced, if you want to run something that utilizes the entire machine, you need to design some parallelism that's at this kind of level, and you have to be ready for the debug jobs at this kind of level also, trying to make sure that your program is generating information that is useful to the scientists. So as you can see, the gap to make this really useful for the scientists or the engineers, for them to provide better solutions for cutting edge problems, is of course the application software. You need to provide all these kinds of application software that is highly efficient, highly scalable. In other words, that is suitable for this kind of machine, and then that is also capable to support the users to explore new stuff on this supercomputer. So in this talk, my example is more on the Earth science side. As you can see, some of you might see this figure before. This figure I borrowed from the Earth simulator, the very famous Earth simulator in Japan. I think this is the real photo of the machine. And then this very nice photo shows the purpose of building this machine, of course, trying to create a digital Earth so that we can use it to simulate different kinds of activities happening on the Earth. And we can analyze both the simulation data and the observation data. And we try to provide our understanding of the underlying mechanism that lead to all these different kinds of changes of the Earth system environment. And by doing that, we can then, of course, the ultimate goal of doing this is to provide the capability of making predictions into the future, right? So that we can, write reports to the politicians and telling them, what should be the right way to mitigate the effects that are involved with climate change. So here is just a quick introduction about the co-evolution history of climate modeling and supercomputers. I actually get to know these examples after I returned to Tsinghua, and after I started to sort of focus on the domain of climate modeling. I think you guys must be very familiar with the machine ENIAC, right? Some people think it is the first electronic computer in the world. And weather simulation actually happened on this ENIAC machine. And this very famous computer scientist, von Neumann, also participated in this activity. Now, the model at that time is quite simple, okay, to simulate the weather. Maybe I think their experiments was trying to simulate the weather for the North America region, and they only have 2 vertical layers. So if you are going to simulate the atmosphere as grids, okay, so only 2 vertical layers, and the horizontal resolution is something like 500 or even 1,000 kilometers, something like that. So you can imagine it's very coarse simulation, but it's already possible at that time. And what they managed to do is to simulate 24 hours in 24 hours. Okay, so marginally they can make predictions, but the results were not very accurate. So they don't think it's very informative at that time. But that's a very amazing starting point for all these kinds of stuff. And then NCAR is the National Center for Atmospheric Research in US. Is one of the leading agencies in the world that perform climate-related research. And Cray-1, this is considered as one of the most successful supercomputer in history. It was, of course, it was very fast. And then, maybe the Cray company has sold it to over 100 customers or something like that. I would be superbly happy if we can sell Sunway TaihuLight to another 4 or 5 customers, right? They have 100 or something like that. So it was a very successful supercomputer, and NCAR was its very first customer. Okay, so the first Cray-1 system installed at NCAR to support their climate modeling efforts. And then the Earth simulator I've just mentioned used to be top 1 in top 500, and they have 3 consecutive Golden Bell Prize applications. So one of them is also related to atmosphere modeling. And this slide, this figure, actually, I borrowed from NCAR's website. It shows a more detailed history about supercomputing and climate modeling. So you can pretty much, if you have known the history of different generations of supercomputer, you can see almost all of them, from CDC to Cray systems to all these different kinds of clusters, IBM clusters, recent clusters using Intel cores, and maybe very recently they're starting to look at GPUs, mics, all these different kinds of heterogeneous supercomputers. So you can see along the history, there are also times that people have to switch to entirely different architectures, right? From the very first vector machines where you only have one processor or maybe four processors, and then you have clusters with 1,000 cores. And then recently they have also started to look at heterogeneous supercomputers with CPU cores and GPU cores. And along the way, so when you switch from one architecture to another architecture, you are going to face the problem of how you actually transit the software from the previous environment to the current environment. So that's pretty much the starting point of my story, the story I'm going to tell you today, the climate modeling efforts on Sunway Taihu-Light. So the starting point in the year of 2015, at that time we know little about the model. Okay, I know little, I know something, maybe little about the model. I know what it's like and what are the major components, but of the over 1 million lines of code, maybe I've read, I don't know, less than a few thousand lines of that. And also at that time, the Sunway Taihu-Light supercomputer was under construction. Okay, at that time we started the project. The machine was also kind of not very familiar to us yet. So we are facing all these different kinds of challenges when we start this research project. The first one is, of course, is very complex application code, millions lines of code, heavy legacy. It's different generations of code. Fortran 77, Fortran 90, and Fortran the newest Fortran 2003. All these different generations of Fortran language you can see in the program, and obviously they were developed. The codes were written by different generations of scientists and developers along the way. So it's very complicated code that you want to sort of port to a new architecture. And for the climate system model, or they call it Earth system model these days, you don't have a very big hotspot. If you do a profiling of the program, you try to figure out which parts are consuming most of the compute cycles, you will find no hotspot, or you find hundreds of hotspots, right? Because there are so many different parts, there are so many different processes that people try to simulate. You have the dynamic parts, you have in the physics, you have a few dozens of them. You have to describe the cloud, describe the rain, the convection, all these different things. They come with their own modules. So you don't have a clear hotspot. And then, of course, the biggest challenge is that the code were, at the starting point of our project, most of the code were designed for the previous multi-core x86 clusters. Okay, they were the way they parallelized the code, the way they optimized the code were for the previous generation of architecture. Now our supercomputer, Sunway TaihuLight supercomputer, is quite different, as I mentioned earlier. So there's this big misfit between the design of the code, the design philosophy of the code, and the new architecture. The fourth part is actually to run the program to make it really productive on the supercomputer is not just a problem of the computing part. If you are familiar with climate modeling, usually people want to run the climate models for like a few hundred years, okay? And that amounts to, you have to say, take up 1/3 of the Sunway TaihuLight supercomputer and run it for several months. And you have to generate, say, several petabytes of data. So it involves with all the different aspects. The machine could be, for this kind of a job, sometimes it could be very unstable. You need to make sure There are different mechanisms that you can apply to monitor the system to figure out which nodes are not at a good status and to improve that. And you need to look at the MPI problems. For some of the settings, you have to customize some of the MPI libraries for them. And I/O is obviously a big problem, and the compiler part, the runtime environment, all these different things, you need people to work on that. So at the time we start the project, along with the 20 also people that work on different parts of the software, we also have a support team from the machine side. They also in a similar size, because they have to cover all these different aspects of the machine. Now, the one in the last, I think, is the biggest challenge, is the lack of people with both understanding of the supercomputers and understanding of climate models. Obviously, these two items are both very complex. You have to accumulate a few years experience to really work on them in a productive way. Okay, so this is the starting point I've mentioned. Maybe Torsten has seen this slide quite a few times before, I guess. With some of the photos, you should be able to recognize some of the people working on the project. So I think this is in the summer of 2015, we have organized this team. So we don't have people who are already interdisciplinary, so we have to set up an interdisciplinary team. So we have people from computer science part, and we have people from the climate scientist part. Especially we have this, you probably can't see it very clearly, Professor Wang Nanning from Beijing Normal University. He's our leading climate expert, which turns out to be also the leading debug expert. So every time we saw all these kinds of error messages, which we don't understand, we forward them to the climate expert, and then they look at it, and then they can tell me, you should look at the dicor part, or you should add the convection part, or something like that. So that's the starting point. It's quite challenging. As I mentioned, we are getting used to the machine, the new architecture of the machine. And along the way, we have to learn the different things about the climate model. And the latter part is obviously more challenging, because I think in this group, I think maybe over 80% of people come from the background of computer science. And we have been working on this project very intensively for 3 months. Okay, so you can imagine it's really intensive. Otherwise, you can't be able to port the code onto the supercomputer within 3 months. So everybody have to work like crazy. The good part is that we have accomplished the goal. Okay, we even have this nice animation made from the first 3 months months work. But then the bad part is, I guess only 2 or 3 or 4 of them, the students, were still willing. Maybe I should not use the word of willing. We were still able to persuade them to continue working on the project after the 3 months. Most of the other students, deep learning is already starting to take off at that time. So they were, compared with understanding some code, I can never understand. I would I would prefer to work on some deep learning programs, right? So as I mentioned, that was the biggest challenge we were facing at the starting stage, because we don't have understanding of the code, and that makes the process very challenging and not so pleasant, especially for the students who are just getting started their research process. But the ones that remain, I think after the first stage, once you get more familiar with the code, you get more understanding about the climate problem, the thing actually becomes more interesting, because obviously it's still one of the biggest challenges in the world, trying to understand the climate, the weather, and trying to make good predictions into the future is inherently very challenging. Both scientifically and or as an engineering problem. So that's the starting point. And then in the following year, we start to accumulate all our experience about the Sunway TaihuLight architecture. We still don't know so much about the model, but we were trying to do something even more challenging. So this is our first paper on this project. So you see many authors, because you have to involve a good number of people to work on a complex program like this to port it into this new supercomputer. So this is still at a relatively early stage. What we try is basically refactoring and some kind of optimizing of the performance. So this figure actually shows our basic methodology, or say our basic workflow to work on this problem. So we divided the major computation part. We divided into two parts. So the first part is the die core part. Is the dynamic core, which simulates how the energy, how the water is transmitted along all these different regions in the world. And this part is relatively well organized. Okay, so the version of the code has been rewritten, I think in the after the 21st century. So it's a relatively new code and well organized code, which means we can actually read the code and try to understand them. Okay, so for this part, we actually did a lot of manual transformation of these loops. We reorganized these loops, and we also did some manual OpenACC parallelization and optimization on the code, on the data structure. So basically, we transform the loops. We try to get the right level of parallelism, and we try to get the right level of say storage for especially faster storage for intermediate variables to be stored in the faster buffer, because that's also a major challenge of the Sunway architecture. For the 64 computing cores, each of them, they don't have L1 cache. Instead, each of them has 64 kilobytes of scratchpad memory. So if you have read some of our Sunway TaihuLight papers, a lot of the optimization is happening in this part, in this 64 kilobytes scratchpad, because we have to decide what kind of data to be stored into the buffer and in what kind of a schedule to store them. So that's a major optimizing efforts that we need to perform on this supercomputer. So that's the die core part, and the second part is the physics parts, which involved all the different physics processes I've mentioned. And this part, the code is not so easy to understand. So for this part, we are basically doing the transformation based on the tools. What we pick is the ROSE framework. So we try to use the ROSE framework and trying to develop some source-to-source transformations. The purpose is the same. Okay, it's trying to transform the loops to the right size for the architecture. The right size means two parts, as I mentioned. One part is for the right level of parallelism. You need to have enough parallelism to fit into the 64 cores. The second part is the memory. You need to think about the 64 kilobytes scratchpad. So this is the results. This is the result we got after we did the refactoring efforts. So the code can already be run in parallel at the million core scale, and the simulation speed is 2.8 simulated years per day. It's not very high, but it's a good starting point we could be using for this kind of climate modeling stuff. Okay, so that's after the year of 2016, and then in the year of 2017, that happens along the way. So I was trying to see if I can get something to excite the group. So we were saying, we have already spent so many time and efforts on this. Why don't we try it to do it really big, right? To run it so efficiently that we can use it to compete in the Golden Bell Prize competition. So that's that obviously that motivation convinced some of the brilliant students to continue working on this program for another year, trying to improve the performance. So this is a stage that we pretty much have accumulated all the different kinds of optimization techniques that we know would work for this new supercomputer. But still, we don't know so much about the model. But whether we know that or not, we have to start, dive into the code parts that we can't understand so much, but we still want to do optimization to improve the performance. So this is the paper that was is one of the Golden Bell finalists. There are more people working on this than the author list, but the Golden Bell finalist paper have this limitation of 12 authors. So they're actually more than that. So this is what we did in the year of 2017. We were trying to do something even more aggressive. Okay, so we have to, so previously we were mainly relying on the OpenACC programming interface, trying to do something based on loop transformations. That would solve some problem, but then that also have some limitations. Some of the hardware architectures of this new supercomputer, we can't really take advantage of. For example, this 8x8 core array, if you want to use this very efficient register communication among these different cores, you have to write your own threading instructions. So that's what we did in this in this second stage. We were rewriting some of the codes from Fortran to C++ to C, I think to C, and then we tried to use ACE-RAD to really to do the fine-grained redesign of the code. The advantage is, of course, firstly, we can have a finer memory control of all these different data items. We can decide which part to put into this fast buffer and in what kind of sequence to put into these instructions. And the other part is we can achieve very efficient vectorization. So these things are given a lot of performance along the way. And then is, of course, this register communication feature that we can use to, especially for Halo-like operations, we can get very efficient communication among the threads. So this is the results after the second stage. So there are 3 bars about performance we shown in this figure. So this one is the performance, the original performance on the Intel core, on one Intel core. The first bar is actually our starting point. So right after we port, we accomplished the porting of the code onto the Sunway TaihuLight. And at that time point, we are only using this management core. We are not even starting to do multi-threading yet. So this is only using the master core. You can see the performance is, in some cases, 1/10, 1/5, or 1/3 of an intercore. This is a kind of what we expect, because the Sunway core is a RISC core. It's much simpler than the intercore. So the performance is also lower. The frequency is also lower. So you can expect is only 1/3 or 1/5 or 1/10 in some of the cases. The second bar is after the refactoring, after the OpenACC-based refactoring. So we are starting to use the multi-threading, the 64 cores to do the computation. So in some of the cases, we are starting to be equivalent to 1 intercore. In some other cases, it's 2 times or something like that. But still, right, you are using 64 cores, and it's only like 2 or 3 intercores. That's not very good results. But that's also what you can expect, because by using OpenACC, you can't really change what we said, the design philosophy too much, right? You are just doing transformation of the loops. The way that you design the data structure, or say the way that you do even you do the parallelizing, is still kind of constrained to the original design philosophy. It's only after you really start to do the redesigning efforts, you write your own threading codes, and you write your own DMA instructions to take advantage of the fast buffer, that's where we start to see some good performance. So for these things, some of them, one core group can be like 10 intercores, or some of the cases for some of the specific functions, it can be like 30 or 40 intercores. So this is after we finish this stage. So it's as you can see, we have modified a lot of the code. We have added a lot of the code, and we have pretty much touched all the kernels that we are capable of touching. The ones that we can find ways to achieve a better mapping of the algorithm to the architecture. So this is another animation we have made is basically trying to simulate the Hurricane Katrina happened in the year of 2005, as you can see, both for the pass, the simulated pass, and this is, we actually have two animations. This is what we see in 25 kilometer resolution, and if you do it in 100 kilometer resolution, you don't see this hurricane that clear. Right. In this one, you can see this this thing in sort of a more clear way. But this makes the team quite exciting, the computer science team. But for climate and weather people, they were saying, okay, so it starts to look like some toy, right? It's starting to produce some sort of maybe meaningful results. But it's important. I think after that we are getting sort of more attention and sort of more climate scientists could be willing to work on the problem with us. So this is after the Golden Bell finalist work. So firstly, in the summer. Okay, we always want to do the hard work in the summer, it seems. In the summer of 2018, so actually you can see the author list. This pretty much covered maybe more than half of the professors in my department. I'm from the Department of Earth System Science. So climate modeling is obviously one major topic that people are working on in my department. So this almost covers, I think, at least over half of them are involved in this paper. So in that summer, the climate professors, they came to our center and worked with the engineer and trying to port the CESM. This is the Earth system model that my department is trying to develop. So we have then transferred the porting and optimization techniques we have accumulated onto this new model. The good part is that this model is also kind of based on the CESM model, but of course it has integrated all these different new processes that these professors have proposed. So in the summer of 2018, we have again made CESM run very efficiently on Sunway Taihu-Light. So after that, they could use the machine to really run all the 100-year, or even I think one of the experiment involves running the model for 1,000 years, something like that, to run all these different experiments that are required for the CMIP, the intercomparison project for all these different climate models that developed by different groups in the world. So they were able to really take advantage of the supercomputer and finish all the experiments and to provide the results to the international community for people to compare among these different models. So that's in the summer of 2018. And then from the year of 2019, we were starting to collaborate with the climate scientists from Qingdao. So there's this National Lab for Ocean Science and Technology in Qingdao. So obviously a lot of people there also care about climate. They also do modeling of the climate. So these people, and also they have very close collaboration with NCAR. So in this work, we finally get a lot of support actually from the climate section in NCAR. I mean, in the Golden Bear finalist work, we also get some very good support from the computer scientists in the NCAP part. And in this part, we get both from computer science section and also the climate section. People are interested about the model we did on Sunway, and they want to use it for some very interesting climate modeling experiments. So in this time, actually, we had some setback in this project. The first problem is that our previous efforts, so this is some challenge when you port some program to a new architecture you are going to face in the early stage. Our previous efforts were using the CESM 1.2 version. And then in this project, people want to use some newer version. It's 1.3. Firstly, I thought, okay, from 1.2 to 1.3, there should not be so so much change, right? But then actually, when we look at the code, we have to pretty much, especially for the atmospheric part, we have to pretty much redo all this refactor and re-optimizing, redesigning efforts for the CAM part to make it again, because they did a lot of modifications to the dicore part and the physics parts of the CAM version. So it's like I think the previous version we work on is CAM 5, and now they have CAM 6. So you can see this obviously from 5 to 6. There's a lot of change along the way. And then after that, we did a lot of work. After we sort of copied the previous efforts we did for CESM, especially for CAM. Now, of course, this time we optimize both CAM and POP with collaborations with National Supercomputing Center in Jinan as well. After we sort of copied these efforts, we find out some of the system functions start to become the bottleneck, like the MPI functions, even the memory malloc functions, all these things. So one reason of this is that the previous programs, they were not designed to be scaling up to, say, 60,000, 70,000, or more than that kind of parallelism scale. So even you just start to initialize your code, there would be a lot of problems when you say read a file and try to broadcast it to all these different processes. When the parallel scale becomes much larger, there are new problems that you need to think about. And load balancing is also, of course, an issue that you need to think about for different kind of parallelism level. So we did a lot of a system level optimization to further kind of improve the performance. So I think at the end of this project, the simulation speed of CSM on Sunway is kind of already acceptable to scientists. So if you don't do very heavy I/O, we can support up to 5 simulated years per day. Okay, so that's important, right? If you want to run the experiment for 1,000 years, you can still finish it within a year if you have good luck. So that's a very important number. Okay, so I will also talk a little bit about the results. As I mentioned, this project, we are based on the CSM 1.3 version, and we are using the Sunway TaihuLight to support the experiments. So this is what we have finished so far. I think there should be more than that by now. But in the paper we have recently published, we have 500 years of pre-industrial simulation is what they call the PI control, and then 250 years historical and future climate transit simulation, that is from 1850 to 2100. So these are all simulated at a relatively high resolution of 25 kilometers for atmospheric model, and then 10 kilometers for the POP and sea ice, for the ocean and sea ice model. Okay, so this is, again, we made an animation to show sort of the detailed information that we can kind of capture in this kind of simulation. So here I'm just going to show you maybe another 2 or 3 figures to kind of highlight some of the interesting parts, the interesting results that you can get from this kind of long period high resolution simulation of the climate. So the first thing is, of course, the temperature, right? The climate change, the global warming stuff, the temperature, the change of the temperature is always one of the key things that people will look at. So here we shows curves of two kinds of different temperatures. So one is SST, the sea surface temperature. So this red one is the high resolution results. And you can see this green and these two ones are what we call reanalysis data sets. That's sort of the thing, maybe not identical to the true value, but it's the closest thing we can get to the true value. So you can see it's kind of compared with the lower resolution is much closer to kind of this similar to observation values. Okay, and the other set is the T2 meter. So that's the temperature at the 2 meter height. You can also see that the high resolution one is basically getting much closer to the observation data sets. Okay, so another thing I want to talk about is the tropical cyclones, right? When you do high resolution, a good part is that you should be able to capture these tropical cyclones in a better way. And then you can sort of try to, so there's a Professor Lin in my department, he's especially interested about typhoons and hurricanes. So these would provide some very interesting, rich data sets for them to study this. And again, if you look at so the first one is observation. Okay, it's the observation from the year 1950 to 2018. You can see sort of the trend. And the one in the middle is the high resolution results. And the one, the lower part is the low resolution results. You can see for a low resolution, these tropical cyclones are largely underestimated. If you look at the number, okay, it's largely underestimated. If you and now for high resolution is slightly overestimated, but again, it's showing a lot of patterns that are sort of more similar to the observations. Especially, I think, especially for this part, the east coast of the North America, you can see it's doing a much better job to capture some of the tropical cyclone events in the simulation. So this is actually for my personal group, we're looking at the code and trying to see, because NCAR people have already done something to trying to introduce some of the AI-based data analysis things into the simulation results, trying to capture these things, and that's something we have to do, right? For this kind of simulation results, is over petabytes of data, which means if you want to just do a simple sweep of the data, it's going to take a lot of computing power, and obviously the traditional drawing the figure and then the scientists look at the figure thing is not going to work very efficiently in this kind of a scenario. So some of the group of people are now sort of moving from purely simulation topics to data analysis topics, trying to develop some of the more efficient tools to do this kind of jobs. Right. So this is the paper that introduces about this new data. If some of you might be interested, you can. It's a very long article. It's a very large data set. So it tries to cover all these different aspects. Okay, so my last slide is just some information for the people who might be interested to spend some time in China, right? As postdocs or just as academic visitors, researchers, both should work. But for postdocs, we're especially looking for postdocs at this time point. We have all these different topics that you should be able to work on: the HPC applications, the data analysis methods, and software tools. And yeah, you are going to be receiving sponsorships from both Tsinghua University and our Supercomputing Center. So any of you might be interested to come to China, write me an email. Okay, so with that, I should end my talk. So this is actually a photo that I took in Switzerland the last time maybe the time before the last. I came for PASC. Yeah. Okay, thank you.
Haohuan.
Thank you.
This was a fascinating talk. I especially like to see both the research and the actual practical issues involved with making something like this actually happen. So thank you for that. And I just want to give a quick advertisement for our next SPCL BCast talk, which will be on the 11th of February at 6 p.m. Zurich time, where Jeff Hammond of Intel will discuss evaluating modern programming models using the parallel research kernels.